In this video, I will talk about pigeonhole principle. This pigeonhole principle has many applications, although it looks a very simple model. So let me just explain what is the pigeonhole principle. It is, it is obvious that if you have, for example, five pigeons. These are the five pigeons. And if these pigeons reach at their place to sit in the evening, and you can see that there are four places. We call it the pigeonholes. There are four pigeonholes and there are five pigeons. When they sit in the pigeonholes, or they actually go to the pigeonholes, then there is at least one pigeonhole in which there are more than one pigeon. For example, for this one pigeonhole, we have one pigeon. For this two, we have pigeon number two. And then for three there are one and four, there are two pigeons. And for this pigeon number four, there is only one pigeon. So it means that if I formally write this principle, then this becomes if k plus 1 or more objects are placed into k boxes, then there is at least one box containing two or more objects, right? So this is called the pigeonhole principle. It has also a consequence. The consequence is that if there are more pigeons, for example, here you have more pigeons, and there are less pigeonholes, you cannot draw one-to-one correspondence. You cannot draw one-to-one correspondence. It means that if you make a function, then this function will not be one-to-one. According to this principle, if we generalize that, for example, if we have box 1, box 2, and box 3, but there are two, for example, balls, or maybe four balls, it means that there should be more than one ball will be placed in the box. This is pigeonhole principle. This principle is introduced by Dirichlet, famous mathematician. This is also called Dirichlet drawer principle. Dirichlet drawer principle. Let me just talk about some example over here. There are many examples that you can discuss, but I will talk about only two. Suppose that there are 6 people Now the question is, must be at least two who were born in the same months. If there are six people, one, two, three, four, five, and six. The question is, these six people can be born on the same month. The answer is no, since the first person can born on January, then he can born in February, March, April, May, and June. So it means that it is not necessary that the six people can born on the same month. They can born on the same month, but the possibility is very less since there are more options. And since there are same pigeons are person over here, and the months are the pigeonholes. Not pigeonhole in this sense, but you have the same people and the same months. Now look at the another example. If we have 13 people, now the question is, must be at least two who were born in the same month. Now this is interesting. Now, if you have 13 people, suppose we have a set of 13 people, and these 13 people are from x1, x2 to x13, and there are 12 months. So there are 12 months. 12 months. Now, first we identify the pigeons. The pigeons are the number of persons. 13 people are pigeons. 13 people are pigeons, and 12 months, which are pigeonholes. So it means that we have January, February, and so on up to December. So you can make a function, for example, b. That function takes a value from 13 people, bxi, for example, and then you get birth month. So it means that there are 13 people, there are more pigeons, and 12 months, there are less pigeonholes. It means that in 1 month, there can be at least two people who born in that month. That is one consequence of the pigeonhole principle. Now, this is another very interesting examples. Among the residents of New York, must there be at least two people with the same number of hairs on their heads? Why? Now, this is going to be interesting. The question says that if we have residents in New York, they can be in any country, any city. In New York, there are people living there, and at least two people must have the same number of hairs in their heads. First of all, let me just talk about the number of people living there. For example, the population is around 8 million. 8 million people living in, suppose, New York. That's the correct spelling. So 8 million people living here. Now, according to the study, the maximum number of hairs on any person's head can be 300,000. That is according to some study, that the people can have at least one person has at least these number of hairs or less than these number of hairs. So our set will be this is 0.3 million. Okay. Now, if for example we make a set, the residents of New York are denoted by x1, x2 up to xp, and then we have number of hairs can be 0, 1, 2 up to 300,000. Since there are more pigeons, these are the pigeons, and these are the pigeonhole. So it means that there must be at least two people who have the same number of hairs, since there are less hairs. So if you make a set, these are the residents, pigeons, and these are the number of hairs. For example, 0, 1 up to 300,000. And these are the population x1, x2 up to xp. So in that case, we have h. This h is each x on xi, and you get number of hairs on xi's head. Okay, that is the case. So these are the pigeons. So it means that there must be at least two people who have the same number of hairs in their head. Now, the last thing that is left in this pigeonhole principle is the generalized pigeonhole principle. The generalized pigeonhole principle says that if, let me just write first, the generalized pigeonhole principle, if n objects are placed into k boxes, then there is at least one box containing at least n by k ceiling function objects. Now, this is very interesting. The consequence of pigeonhole principle is the generalized pigeonhole principle, that this says that if you have number of boxes, for example, 2 boxes, and there are 3 objects, then this principle says that that you can count in how many balls or objects can be placed in one box. Minimum number of balls we can have in one box. For example, in this case, there are 2 balls over here. So this is called generalized pigeonhole principle. And remember that this thing is called the ceiling function that we study in calculus. Let me just give you a very simple example. Suppose we have 100 people, and out of these, how many are born on the same month? How many born in the same month? So in this case, we have n is equal to 100 and k is equal to, for example, since we have 12 months, so n by 100 by 12 give us approximately 8 point something and 8 point something, 8.3 for example, the ceiling function says that the value will be 9. So there will be at least 9 people who have birth month in the same month, whose birth month is the same. Thank you for watching.